Hello friends. So as I was discussing about air friction, I would like to give you another problem related to air friction. Suppose a block is at a height h and from top it's being just dropped, and when it touches the bottom its speed is 1.2 root under gh meter per second. Now what is the work done? Say its mass is m. So what is the work done by the air friction? Suppose the air friction is there in the process. So how do we approach? First thing we can do is that at the top point, what is kinetic energy? 0. No motion, kinetic energy 0, velocity 0. Just at the point when it was about to touch the ground, its velocity became 1.2 root under gh v. So what is delta kinetic energy? It is half m v square. It means 1.2 square, so 1.44 gh minus 0. So that is 0.72 mgh. So this is the change in kinetic energy. Now what we have studied, that work done by all forces, that is equal to change in kinetic energy. So in this process, in this track, what were those all forces? There was simply work done by gravity and plus work done by air friction, and that is 0.72 mgh. So what is the work done by gravity in this point? Displacement h downwards, gravity also downward, both coming downward, h also down, mg down. By h here I mean the displacement. So initial position is this, final position is this. So displacement direction is downward, final minus initial, downward. Simply gravity also acting downward. So work done by gravity will be simply what? mgh cos 0 plus work done by air friction, we don't know, and that summation is equal to 0.72 mgh. So it means that work done by air friction will be 0.72 minus 1 mgh. So that is minus 0.28 mgh. So such ways can also be adopted while solving work done by air friction. So especially if the force is unknown, sometimes problems are asked that what is the work done by a special force which is unknown, any force which is unknown. So what we do? We don't go for directly solving the work done by that force. What we do is we calculate the entire work done, especially in the form of change in kinetic energy, and then we subtract the work done of the given forces, because displacement would be given in the problem. So we subtract the work done by other forces, and finally the last amount of work done which is being left out, that is because of the unknown force. So similarly we did here. There can be any third force also whose magnitude would be given to us. So we would add it here, and then again we would subtract it, and we will get work done by air friction. So this way we solve such problems. Now we'll do another good but simple problem also. But this is a block of mass m, and the coefficient of friction between the block and track is mu. So suppose a force is acting like this at an angle theta with horizontal. Force F is acting, and this force is ensuring that the block is moving at a constant speed on this track. So again, the catch point, constant speed. So the speed is constant along the track. It means force external, horizontal, or just like x, will be 0. Force net external. So suppose the object moves a distance d. Then what would be the work done by this force F on the block? So how would we calculate? One thing we know, because it's given that the velocity is constant. So one thing we know is that if cos theta, it means its component along x, f cos theta. F cos theta is just equal to what? It is equal to the friction force. Object has a tendency to move in the rightward direction, so friction would be in leftward direction. So that is friction force F. And since the object is moving, so it means it's a kinetic friction. So we can replace F by mu. Now, the most interesting point is calculating this N force, normal. We know by definition that friction is equal to mu N. So what is this N? In single flow, without taking into consideration the actual meaning of normal force, we can simply write N is equal to mg. Will it be correct here? When do we write N is equal to mg? When there is only one block and there is a force in external direction, horizontal direction, there one or more than one forces, and then we simply say that the normal acting here is just equal to mg. Because mg is the amount of force which the earth or the ground, the base level, needs to apply on the block to balance its gravitational force. But what is the difference here? The difference here is that the external force has a normal component as well. So the best way is, let's draw the free body diagram, take into consideration all the forces, and then go for solving N. So suppose whatever N is, definitely it's not going to be mg here. So whatever N is, N is supplied on the block by the ground should be in upward direction. That it would be. And its weight is mg, downward direction. So we just know that this object is in equilibrium in y-axis also. It's not moving up or going down. So we simply can replace as Fy is 0. Summation Fy is 0. It means that N plus F sine theta, that would be equal to the downward force. That would be equal to mg. So N is basically mg minus F sine theta. So now we will replace in this direction, in this value, we will replace N by mg minus F sine theta. So what we get finally? We get F cos theta plus mu F sine theta equals to mu mg. So if we need to take one out F, it would be mu mg by cos theta plus mu sine theta. So this is the value of F. So rest all is constant, theta, mg, mu. Now this is the force F along this. Now if we are asked find the work done by the force F when the object is moved by distance t, so what we will do? We will calculate work done equal to F d cos theta. Simply, this is the angle theta. So it would be mu mg d cos theta divided by cos theta plus mu sin theta. Simple. So in every problem we have to go by basic. Now keep in mind that generally problems in IIT or IEEE, almost 99% problems, they are two-step problem. They are not going to give you a direct formula-based problem in most of the cases. You would require formula, but at the second stage. At the first stage, you have to find a catch, a simple catch. Just like here, you have to calculate n correctly, that what should be the proper value of n. In other problems, there would be different catches. So, all you need to do is keep your mind open. Don't just stick to any formula. Just look at the situation, what's happening, and solve accordingly. And take it from me that the questions these days are actually really simple one. They're just checking your basic concept, that's it. No hi-fi problems. Fine. So, I hope this must be clear to all of you. Now let's solve another simple problem, but actually very important one. Those types of problems have been asked very frequently in JEE in previous papers. So suppose this is a center point, there is a thread, a string, and a block of mass m is being attached at the bottom. Now it's asked that what should be the minimum velocity imparted to the ball so that it moves up and complete a circle. Generally, you see what? This is the resistor. I hit here, it moves up, comes down. You have to give such an impulse at the bottommost point, it completes one circle. So for completing circle, it should come first at the topmost point. If it comes at the topmost point, half of the work is done here. Then the rest of the part, it could easily track by the virtue of gravity. The problem is, as far as you are going opposite to gravity, in sending up and up. Once it's at the topmost position, it will very easily just trace the track. So what concept we need to apply? We'll go by simple basic energy equations which we have studied. So first thing, that here gravity is under consideration. So potential energy would be required. So solving potential energy problems, we are independent to take any reference frame. Just we take that this point is, this line is potential energy 0 line. At this line, potential energy is 0. So what will the potential energy here? If suppose the length of the string is L, it means this height is 2L. So potential energy here is mg h mg 2L. Suppose we impart a velocity v naught to the ball. So what will be initial kinetic energy? Half m v naught square. So total energy would be half m v naught square plus 0. Just half m v naught square. Now when it reaches at the topmost point, it can have a velocity v. So it will have some kinetic energy half m v square plus potential energy mg 2L. Now apart from gravity, is there any external force? There is not. Just gravity is the only external force. And this force which has given it the momentum, that is acting just before the commencement of the problem, before starting the track, before starting the motion. So this force which is giving the impulse, that is acting till the starting point of the motion. Once the motion starts, this force is nowhere into consideration. This force is not in contact with the block M. The block M is totally free. So its job is to give this kinetic energy half m v naught square. That's it. Once it has been given, it will keep store that energy. So as the block moves up, at every instant, what is happening? That its height is changing up. So gravity is acting on it. So gravity is doing a work that is simply minus mg12. Simple. So that work is changing its kinetic energy. So ultimately, there are two ways to say the same thing. One is that gravitational work is changing kinetic energy half m v naught square to half m v square, and the negative of the work is minus mg. Negative work is basically minus mg12. The other way to say the same thing is that as the block moves up, then at every instant its kinetic energy gets shifted to potential energy because of the virtue of gravity. So that shift is mg12. So ultimately, we are taking this energy mg12 as a part of the energy of the block. So gravity is basically part of the system. It's not an external force anymore. So since it is a part of the system, then only we can write that half m v naught square is equal to half m v square plus 2 mgl by the law of conservation of energy, because we considered gravity as a part of the system. If we do not consider it, then what we will write? We will write half m v square minus half m v naught square. That is the change in kinetic energy. Or in another way, you can write half m v naught square minus half m v square. That is 2 mgl. Also, like this, if you write, what will be negative? Gravity acting this way displacement in up way. So it will be minus 2 mgl. So if you just arrange it, we will get half m v naught square equals to half m v square plus 2 mgl. So this and this same. This has been derived from law of conservation of energy. And this statement has been derived from work energy theorem. The only difference is that when we are writing this expression, we are taking gravity part of the system. So when we consider something a part of system, it means its force becomes internal force, and that too is a conservative force. So what we will do? A conservative force just changes the potential energy, and the same is doing. Or if we consider out of the system, then it will do a negative work, and that will be nothing but give the same result. Fine. So for our problem purpose, the first expression is more than enough. So we got this relation. Half m v naught square is equal to half m v square plus 2 mg. Now what else? It's a circular track. It means centripetal force is acting everywhere. So at the topmost point, what are the forces downward direction? T as well as mg. So what we know? That centripetal force is mv square by L. It means T plus mg equals mv square by L. So mv square by L. So this mv square can be replaced by we just cancel this 2, 2, 4. So mv square can be replaced by mv naught square minus 4 mgl. By L. So in this case, what we see? We can see that for the system to get a minimum negative, just a minimum velocity to attain this circular motion, what we can afford is that at the maximum highest point, this tension can go to 0. Before reaching this point, if this tension goes 0, then object will slag and it won't complete circular track. It will slag, or it will slag here. It should not slag before coming to the topmost point. Even if the topmost point it slags, then because of the velocity, this object will try to continue its motion and it will again complete the circular track. But before this point, it should not slag. So at the maximum point, this t can go 0. Then we will get this v0 value to be the minimum possible. So if t goes 0, from this equation, what we get is that mgl equals to m v0 square minus 4 mgl. If we cancel out m, we get v0 is equal to root under 5 gl. So this is the minimum velocity which should be given at the bottom of the block to complete a circular track. The minimum velocity which should be given. So what we saw here, that at the topmost point, this t can be afforded as 0. If this t is 0, then because of velocity, there is some velocity, some v is there. So that v will again retrace its path and it will complete the circle because v is also there. Now, what else kind of problems can be there? That instead of this topmost point, what should be the minimum velocity so that it covers, say, 1/4, or it goes up to at this point, or it goes up to at this point. So in all the different cases, we have to again go by the same concept, that what would be the change in kinetic energy up to this point, and again we will solve the centripetal force problem. We will take into consideration T plus the component of gravity. So the two kind of equations we have to consider in solving this vertical circle problems. The first is conservation of energy, and the second is your centripetal force expression. Just take into consideration these two expressions, centripetal force expression and conservation of energy. We can solve any vertical side. We will see another problems in the subsequent lectures. Thank you.